All right, everyone. This is our class number 24. We're going to apply what we learned from the theory part of principal component analysis in Python. So there are three notebooks that we will be covering today: PCA, which we're doing principal component analysis using a PCA package. It's a Python package, relatively a new one. It was, I think, the first version was released January 20, and it got updated last month. That was the last update. And then this is a package that's built on top of the Sklearn package. And it has very cool visualization features. Then we're going to do the same thing using the Sklearn package. And then finally, we will be replicating the kernel PCA the charts that we saw, the graphs that we saw in the theory lecture. Okay, let's start with the first one. The principal component analysis, we're using the PCA. And guys, remember this is case sensitive. So all are small letters, so PCA. The installation, very simple, straightforward. You can do just simply, it's going to work both on Mac and Windows and Linux, whatever. You just do pip install PCA, but be careful, this is case sensitive. After you have installed that, you can import PCA from PCA like this. And you have to make sure that if you want to replicate, if you want to see exactly the numbers that I see, you have to make sure that your random state is the same as mine, 1000. And we call this number down the road. Okay, let's import the PCA and from the PCA package. I know this is not necessarily the best naming, but whatever. And now let's look at the documentation. So this is the documentation for the function. So basically, the most important thing that we need to know is the number of components, right? So number of components is it the number of PCAs, 2, 3, 4. But this function from the PCA package has a very cool feature, and it says instead of integers, you can pass probabilities, right? Well, percentage. So for example, if I say number of components is equal to 5, so I'm dealing with 5 principal components. If I set it equal to 0.95, what do you guess? What is it? Well, it's going to continue increasing the number of components until 90% of the variation is explained. So this is a very cool feature, right? So if you change it to 80, so it's going to add to principal components until 80% of the variation is explained, right? This is number of features. So for visualization, we're going to play around with these things. So for example, if you have 30 features, but you just want to visualize 2 of them or 3 of them, so you set number of features is equal to 2 or 3. Alpha, standard deviation. So these are if you want to detect the outliers, so you can set the alpha and standard deviation. You can read the documentation, but for the purpose of our exercise, the number of components, maybe the number of features is all that we need. And most importantly, this one. So this is very, very cool that you don't need to use the standard scalar from the pre-processing package. It is already built in this function. If you just say normalize is equal to true, it's going to do the standardization automatically for you. Okay, so we don't need to scale the features manually. All right, and then again, random state. We have to make sure that your random state is the same as mine if you want to get the exact same number. Okay, so let's import that, and I'm gonna. So our goal is to replicate. Let's actually quickly replicate this one. Let me pull up the PDF. Okay, we want to replicate this one. Do you remember we talked about these ones last time? So these ones. Let me see if I can minimize this part of it. No, apparently no. I don't know how to minimize this or the thumbnails. It should be something easy. There you go. And we want to replicate this, what we call biplot, right? We were looking at scores versus loading factors, loadings. So these were the scores are, each state has, we can visualize 50 states based on these two principal components, right? PC1, PC2. And PC1 was a linear combination of murder rate, assaults, urban population, and rape. PC2, the same story. And these were the weights, right? The loadings. We wanted to replicate this one first. So that's why we're working with this USA arrest data set. And let's load the data set. Yeah, as you can see, we have 50 states, and with their the features for all the numbers for these features, right? Murder, assault, urban population, and etc. Now let's go ahead. Remember, guys, this is our unsupervised learning model, right? There is no y variable here. We're not trying to predict anything, right? And because the state itself, the name of the state has nothing to do with our principal components, I'm going to get rid of them. So this is our feature space X. So we define it as everything but state. And for visualization purposes, I'm going to save the states as states, right? Because I'm going to use them later. Okay. So our feature space is basically 50 by 4, and these are the features, right? 1, 2, 3, 4. Now, when you load this the PCA library from PCA package, application in Python is very easy now. So you can build a model. Let's train a model, and by calling this function, I'm going to say that PCA number of components. I'm going to start with 4 because I have 4 features. Let's start with 4 principal components as well, right? And then when we want to visualize it, we will reduce the dimension to 2. And this is very important. Normalize is equal to true. Because the units are somewhat different, right? So this is 13. You can look at the averages. So this is in the scale of maybe 10. But this one is very different, right? Maybe 300 or 250. Because the scales are relatively different, you have to normalize. But if these scales were close to each other, you can skip this part and just let it not to be normalized, right? But you get the idea. So here we're going to use the standard scalar as a normalizer. So by default, it's going to use the standard scalar, our z-score transformation. The number of components is equal to 4. So if I run this line, now the model has been trained, and I can look at the results. So results, for looking at the results, I will do model.fit_transform x. So this fit transform is like every other machine learning that we have worked with, right? Fit the model, use train set, and then transform. Why we're doing fit transform? Because remember, we want to generate the scores, right? We want to go from these numbers, for example, for California, these numbers, to principal component numbers, to score numbers, right? So that's why we have to do fit transform. If I run this line, it's going to take a second maybe. And then behind the scene, let me actually reduce this line. Behind the scene, we can look at the results output. So everything has been saved to an object. We just named it result. Let's see what is inside the result. So result, as you can see, is the dictionary. So these are the key. For example, we have loadings. And so basically we have, because we chose 4 principal components, we're going to have 4 loading vectors, right? And then if you look at the PC, so this is how you extract from a dictionary, right? If I just do results dot loadings, it's going to show me these 4 principal components loadings, right? If I say the results dot PC, basically it's going to give me the scores. So these are the scores. Let's see, what else do we have? Explain variance, right? So this is our, so the first component is going to explain 62%, and it's cumulative. It's cumulative variance explain. So the first 2 principal components, 86%, the first 3, 95%, and the first 4, 100%, right? Because we have only 4 features. And the model is PCA with the number of components, scalar is a standard scalar, and etc. Right? So you can, again, we are not interested in outliers, but just know that if you use PCA from this this Python package out there, it can automatically compute the outliers for you as well. All right, but because we don't like this kind of ugly output, we're gonna go ahead and construct our own ones and give them properly named and run. I'm gonna make an object called it loadings, and the loading is going to be the loading part of this result dictionary, right? So these are the loadings. And as you can see, if I have 4 principal components, so these are the loading vectors. These are the phi's. In theory, we talked about it in phi 1, phi 2, phi 3, phi 4. So here we have 2 principal components. If I change the number of components to 2, you will replicate exactly these numbers, right? So again, I'm going to go down the script by doing PC4, and we will come back and do PC2. Then we can score. We can save the scores. Remember, guys, these are the principal component version of the variables, right? So, for example, California, 4 numbers, Florida, 4 numbers, and etc. So these are the scores. And for visualization purposes, I'm going to add the number of states back to the data, right? So, and we save them as a state. I'm going to add it to this data frame to this score that we just created. If I look at the head of the data set, so it says that Alabama, the score for principal component 1, this number, for principal component 2, this number, and etc. Is this a straightforward, or is it clear what we're doing? Okay. Now we want to let's go through the Scree plot and the biplot. So what was the Scree plot? The Scree plot was the plot that showed you the first principal components, well, the first one, second one, etc., and gave you what is the proportion variance explained, right? Or the proportional explained variance, PVE, or PVE in the ISLR language. And as you can see, this package made it very easy for application, right? I just need to write whatever you name it. We call it model. If I go back, so we call it model when we were training the PCA. So we call it model. So now if I do model dot, there are very interesting plots that we can do. And it's as simple as that. If I do model.plot, by default, it's going to give me the Scree plot. And it's really neat, right? So you can see the first component is explaining about 60%, the second one, 24, 5%, and etc. This is really, really straightforward. Again, the Sklearn package, the output, if you want to do Scree plot with Sklearn, you have to manually construct that, which you have the code for that if you wish. Now I have the code for you. We can manually construct. This is exactly the same data set. And if you want to do a Scree plot, you have to do it manually. And this is how we did it manually. Okay. I added the, this is non-cumulative, this is cumulative. So that's why it adds up to 1. But I think this one is a lot visually cleaner than this one. So I prefer to work with this one. This is a new package. Okay. Now we can go back and change those things that we were playing around in the PCA function, right? So let's, for example, look at this one. Imagine instead of number of components 4, I want to see, just go up to a point that 80% of the variation is explained, right? So let's see how does that work. So let's run through the code. So it seems that only 2 components is enough. If I look at the Scree plot, that's where we see that, right? Because this is a threshold that we picked. I wanted to look at how many principal components I need to be able to explain 80% of the variation. And it seems that, no, it says that 2 principal components explain 80+% variation of the variance, right? So this is really, in my opinion, this is really neat. Okay, so that was our Scree plot. Now let's look at the biplot. So what was biplot? As a reminder, biplot displays both the PC scores and the loadings. So the loadings were those vectors, right? So if I have 4 components, principal components, I'm going to end up with 4 PC loadings. If I have 2, I will end up with 2 PC loadings. Okay, and how can we do it in Python? Again, this is the model that you constructed. Simply do biplot, right? If I do biplot, but there are very cool features in the biplot that we can play around with. So these are the features in the biplot function. By default, guys, this is unsupervised learning model, right? So by default, there is no label. There's no label in your data set. However, in this one, I know that the labels, I can at least use the states as labels if I want to visualize them in 2 dimension, right? So that's why I saved those states. I call them states because I wanted to use them here. If you do not put, we're going to play around with and without this y. If I do not put these states, then you will see dots, and that's it. You don't know which is which state, right? But I labeled them. I pass it to the function, and it's going to automatically label it here for me. So this is really interesting. And what else do we have? This is number of features. So if, we'll play on with this one. So I know that I have 4 features. And if you want to see all these 4 vectors, you said number of features is equal to 4. If you want to see the first two ones, you set it equal to 2. Legend, I put it equal to 0, false, because if I set it true, it's going to, well, we'll see. It's going to list all the 50 states here, and the scale is not necessarily clean. And what else? Label is equal to true because I want to see these names here, right? So let's run this. So this is basically a replication of what we did in the theory lecture. So it seems that, so how should I interpret the biplot? So for biplot, these are the directions. So for example, this is murder. And if you look at the arrow, it's like this. So if you go down this road, so the murder is going to increase. Then assault increase this way, rape increase this way, and then urban population this way. So these states, again, guys, remember why are we doing PCA? Because to get some patterns out of the data. So it seems to me that whatever linear combination of the features the PCA is using, but whatever it uses, it seems that these states are in the same, I can put them in the same category. Maybe these states in the same category and these states in the same category. Does that make sense? And I don't know, you see if you can relate to these names here or not. So is it fair to say Florida, Nevada, California, Arizona, New York, Colorado, New Mexico, Maryland, these are in the same category, kind-ish? And then maybe the best ones here, then the murder rate is very low. Wisconsin, New Hampshire, Iowa, Maine, North Dakota, these are all in the same category as well. Whatever, so this is what the data is suggesting, right? So if it makes sense or not, maybe the data is old or not. I have no idea about the date of the data set, but it is what we can infer from the PCA, okay? Again, if I go ahead and get rid of these labels, see, I don't see the name of the states here. Then if you want to see the name of states, you can put legend is equal to true, but the problem is that this is not necessarily visually good. And then, oh, let's see what else I wanted to show. So for example, if I say number of features is equal to 2, it's going to show me the first maybe 2 features. So this is, imagine you have hundreds of them, and when you're visualizing it, you want to see 3 of them, 4 of them, right? So that's how we do biplots using the PCA package. All right, are we good? So that was a replication of the US arrest data set that we covered in the lecture. Now, let's work with another data sets. I'm going to work with a data set called wine. And this is a very famous data set in the machine learning community. Actually, I got it from the UC Irvine, California, Irvine. They have very, I think some of you guys reach out to me that, what if you want to work with data sets, just play around, use them as a sandbox and play around with it, with our the machine learning models that we learned. So UCI is a very good source for playing around with data sets. Kaggle competition, that's very, very good data resource if you want to play around with data sets. And yeah, if you click on this UCI, so these are the most popular data sets since 2007, and usually for teaching purposes, right? So if you watch the lecture videos online or any machine learning courses, most of them are using these data sets. So for the PCA principal component analysis, I'm going to use wine data set. Now let's quickly go through this wine data set and see what it is. Let me load up the data set here. So these are the columns, and let's read through the documentation here. So what do we have? The data sets are the result of the chemical analysis of wines grown in the same region in Italy, but derived from 3 different cultivars. The analysis determined the quantities of 13 constituents found in each of 3 types of wines, right? At the end of the day, we know that if you want to segment these wines based off their characteristic, the features, we will end up with 3 classes, right? But here we're going to assume that we don't know the labels. We don't know, even though in the data set we do, but let's assume that we don't know that there are 3 classes, right? And we're going to treat it as unsupervised. And what are the features? So for example, the features are alcohol, malic acid, ash. Now, I'm not an expert, but you can imagine these are, you can categorize the wines based on these things. and color intensity, hue, proline, and etc. Magnesium, and etc. Right? So those are the features. And the goal is to, let's see, if I want to break them down in principal components, if I use 2 components or 3 components, what percent of the variation is explained? Okay, so let's look at the, let's quickly look at some numbers here. I'm going to, guys, so look at that. There's customer segments. There are 3 customer segments, right? At the end of the day, if I do value counts, we'll see that customer segment 1, 2, 3 are available in the data set. And these are the number of observations. For segment 1, we have 59 observations, segment 2, 71, segment 3, 48, right? And let's look at some numbers. At the very least, I can look at the averages, the difference between averages among these 3 segments, right? So for example, let's call them customer segment 1, 2, 3, and look at the average amount of alcohol. So it seems that in terms of alcohol, they're almost the same, right? No much significant, no, at least economically significant difference here. Malic acid, so it seems that the average malic acid is slightly different. Ash, maybe, well, pretty much the same. But start from this column, we will start seeing differences. For example, ash alkalinity, I don't know what is it, but it seems that they're different. And magnesium, maybe way different. So maybe this is one of those features that's playing an important role for segmenting the wines into 3 categories. Then total phenols. So again, these are different. These are different. Non-flavonoid phenol, I don't know. These are also different. Color intensity. You can see on average, they're different, right? So maybe this segmentation, which in the labeled data is not completely off, but we're going to assume that we do not know these labels, right? So for that, I'm going to go ahead and drop them first. So I'm going to drop customer segments and then save the rest of them as my X. So this is my feature space. And again, for visualization purposes, I'm going to save the label. I'm going to save these customer segments as labels, because down the road, when I want to visualize them using Biplot, instead of Y none, I'm going to use labels, right? You want to see how ex post there, how the PCA is doing a good job or not, right? Then the rest of it is exactly the same as what we did with the USA arrest data set, right? So let's train the model PCA number of components 13. I start with 13 because that's the maximum number of features that I have already, and make sure that normalize is equal to true. I go back to the data set. Do I need to do normalize here? The answer is yes, because we have a scale from, let's say, 0.3 to 100 something. So we have to definitely normalize the data, right? So let's go ahead and train the model. Same story. We can look at the loadings. So we have 13 principal components so far. We can look at the scores, and I add the labels as well. So this is transforming the data from X1, X2, X3 to X13 to PC1 to PC13, right? So with these scores. Now we are ready to visualize something. So with 13 principal components, of course, we can explain 100% of the variation. No surprise here because we have 13 features, but look at that. The first component is explaining, let's say, 38-ish%. Well, we can look at exact numbers instead of speculating. Oh, no. So it's results. Let me see, what did we have? Results. And loading. What was it? Variance explained? Yeah, explain variance. Okay, let me copy and paste it to make sure that we can look at the explain variance. Yeah, so the first component is explaining 36%, and then this is cumulative. Then the first two 155%, the first three 166%, the first four 173%, and etc. Right? So it's doing something, but it's not as promising as the previous examples that we saw, right? So it was not 90% of the. So actually, if I want to explain 90% of the variation, let's try it out. If I want to explain 90% of the total variation, let's see how many components do we need. It seems that we need 8 principal components to explain 90+% of the total variation, right? Now, this is still reducing the number of dimensionality from 13 to 8, but I personally would not do that. You know, if I want to do, if it is not for the sake of visualization, I will not use PCA because first of all, I'm explaining only 80%, not 100%. And secondly, it's not a huge amount of reduction in dimensionality going from 13 to 8, right? So I know that XGBoost can easily handle that. So, and I'm losing interpretability here. I'm losing the name of the features, at least the name of the features. So for that, if it is not because of the visualization purposes, I'm not going to do PCA. Again, you have to see what you want to do with PCA, right? But in this example, we want to do visualization. So we're going to go from 13 dimension to 2 dimension because we are looking at biplot. So if I do biplot now, let's use the biplot function here. And this is how it looks like, right? The real data actually, what you see in real world is this, because guys, I'm going to use this. This is somehow cheating. I'm using labels because I already know what are the segments, but let's say I have no idea what are these labels, right? Can you agree that at least the data is summarized in 3 clusters, maybe 4 clusters, one here, one here, one here, one here, right? At least, maybe, I don't know, maybe 3, right? Let me show you how it looks like. There is this scatter plot that you can do. Let me pull up the documentation here. So scatter, this comes from the PCA package as well, right? So I can do scatter. Let's see, what do we have? So our Y is none, so default, we don't have anything. Let's actually plot this. It's going to take a little longer. So first of all, as you can see, it's nonsense if I have the legends equal to true, because it's going to, every single observation is going to treat them differently. So it's going to give them different colors. So it doesn't make any sense, right? So the first thing I need to do is get rid of the legend. So legend is equal to false. Then even labels, labels is equal to false. Let's see. Okay, now we know that these colorings are just some random colorings, right? I can go ahead and say, change the CMAP. This is the coloring theme. By default, it's going to use set 1. This is a matplotlib thing, right? If I do this for visualization, the CMAP, you will see CMAP. I don't know, if you are doing any kind of visualization, you should know what a CMAP do. But that's basically give you a spectrum of colors, right? So I can, for example, do binary. Just plot these dots in 2 colors, right? But we know that these are not labeled, right? So let's do none. If I do CMAP num, it's going to treat them as none. Well, all of them are white. So this is what PCA did to the data set for us, right? Do you see the white dots? Okay. So I know that if the first principal component is explaining 36%, the second principal component is explaining 19%. And if you wanted, I don't know, if you wanted to segment these ones into number of categories, what is that number? How many categories do you see here? By staring at this. Make a number, make a guess. How many clouds of data sets do you see? Maybe 3, right? So there's a cloud, no, 1 cloud of data set here, 1 cloud here, and 1 cloud here, right? So it says that based on the characteristic of PC1 and PC2. So, and we have no idea how these are sorted, because remember, this is a linear combination of all those 13 features. But whatever it is, we don't care. We want to get some pattern out of the data. So, and this suggests that the first 2 principal components are explaining, what was the number? 55% of the variation. This is not ideal, but still something, more than 50%. And it's already sending me some signals that if you want to do a customer segmentation for the wines, there are 3 classes here. Does that make sense? So this is what we do with principal component analysis. Next class that we do clustering, for example, I want to do k-means clustering. And as I said, one of the caveats of k-means clustering algorithm is that you have to pre-specify k. So this is where I can get the k. I can start with 3, right? Again, one application of PCA, we are going to use it as an input for the unsupervised and supervised learning models. So this is what we see in reality. And then now we're going to cheat a little bit and do the biplot by the labels, right? So here, actually, I can do it here. I can add the labels y is equal to, we call them labels, I believe. Now, if you're wondering, this is what we define up there as labels. These are the labels that we know that there are three customer segments, 1, 2, 3, and this is what we save them up there. So if I do labels, yeah, now I have to make sure that I change these to default, maybe set 1. Yeah, so there you go. So the colorings is there. Now, if you want to see the numberings of the customer segments, so for example, you can do labels equal to true. So this is 1, 2, 3. Because this is only 3 labels, you can do legend equals true as well, because it's not gonna ruin your. So we have 1, 2, 3. So as you can see, PCA is powerful, right? Even if you go from 13 dimension to 2 dimension, it still can tell you how many clusters do you have in the data set, right? So this is another application of PCA. And so the difference between the scatter plot and the biplot is that in the biplot, well, you will see the direction of the whatever number of features that you want as well. So for example, I put 13 here. I want to see the direction of all the features that we have here. So let's see. Let me try to zoom it in and see. So for example, I don't know, alcohol this way. And as you can see, well, it seems that the majority of the data is concentrated here. Do you remember we compared the averages? The average of the alcohol was not that different. So I'm not surprised that the average was not that different. What is different, maybe hue should be different because these guys have higher hue compared to these ones. And then, I don't know, maybe something here and here is way different. What do we have? It's hard to read, I believe. I don't know what is OD, but this is flavor nodes. I don't know what it is, but you get the idea. So if you go maybe instead of 13, I use 3, it's more readable. Yeah, we have ash color intensity. Anyways, I hope that you get the idea. So is this clear? How we do principal components in Python? Let me see how we're doing in terms of time. So let me go ahead and briefly talk about how to do PCA in Sklearn. You don't need to necessarily do that, but if you're curious, you want to see how to do that, you can go over the Python notebooks here, the codes here. But the idea is that if you're concerned about the speed of PCA package, don't worry, because this package is already built on Sklearn functionality, so it's going to be as fast as that one. And I think some people, a bunch of developers from MIT did that, put together this package, PCA. Yeah. At least as far as I was reading the documentation. Okay, so let's quickly replicate whatever we saw here using the Sklearn package. And so this is historically what I personally used to do PCA before that package in Python. So exactly the same data set. This is our wine data set. And here you're going to import the PCA from Sklearn decomposition. And you have to, these are capital letters. Maybe the reason that the author of those packages picked small letters, they want to distinguish themselves from the Sklearn function. So Sklearn use capital letters and they use small letters. Again, you have to pass a number of components. The documentation is pretty much the same because remember, PCA is built on top of Sklearn. And then you can extract number of features, you can extract number of components, you can extract, for example, these are the loadings, right? If you do PCA.components, give you back the loadings. These are, and as you can remember, the output of the PCA was a lot cleaner. It was a data frame, so this is not data frame. It's up to you, right? I think the choice is up to you. It really doesn't matter. It's not that different. You can learn them both very quickly. You can look at the scores. So if you want to, in the previous one, if you wanted to see the score, you have to extract the PC. Now here you have to do fit transform, right? But you get the exact same numbers. For proportional variance explain, however, the Scree plot, do you remember here we did it automatically? We did it automatically. But if you want to use Sklearn package, you have to make sure that you build the PVE first, proportion variance explain. There are 3 different ways to do that. This part is important though, right? I want you to learn this part. Because when it comes to kernel PCA, there is no built-in functionality that it can extract the PVE, proportion variance explain. In the linear PCA, if you're using Sklearn package, you can easily extract the explained variance ratio, PVE, by using this method, right? Whatever you train the model, you save it as PCA, and then you're calling it here. Explain variance ratio, as easy as that. So we have 13 features here, 13 principal components, and we have 13 of these variance explained ratios, right? Very good. So this is one way. Another way is by going back to the definition of eigenvalues, eigenvectors, right? So we can extract the eigenvalues of an eigenvector from the covariance matrix, right? So this part is a little technical, so just I'll briefly talk about it, but it's no big deal if you don't get the mathematics behind it. But for those of you who are interested, in the theory part, we talked about covariance matrix, right? So in PCA is looking at the covariance matrix, calculate the eigenvalues, eigenvectors, and then sort the eigenvalues. The first eigenvalues is going to become, the largest eigenvalue is going to become the principal component ones, and et cetera, right? So we can actually do it in Python as well. So we can save the covariance matrix by calling this method, actually it's a function. This function get covariance, and now the covariance matrix is here. So remember, if I have 13 features, what is the dimensionality of the covariance? 13 by 13, right? You don't know the covariance matrix? Yeah. So if you have, I don't know, if you have 2 stocks, what is the covariance matrix? 2 by 2, right? Variance of Apple, Microsoft, and the covariance of the 2 off diagonal, right? So this is the same story. So we have 13 features. The covariance is going to be 13 by 13. Then you need to use linear algebra class from NumPy, and then you can calculate eigenvalues and eigenvectors by running this. You have to say, okay, from this linear algebra, use this function EIGI, pass the covariance matrix, right? Whatever the matrix that you want to use as transformation. So this is your transformation matrix. Then it's going to give you back the eigenvalues and eigenvectors. So this is my eigenvalues. So if I take eigenvalues divided by sum of eigenvalues, these are the same as proportional variance explained. Does that make sense? Because let's say you have 10 eigenvalues. What is PCA doing? Sort them. And then, so let's say you have 3 eigenvalues, right? And the numbers of 10, 20, just for the sake of argument, 10, 20, 70. What is and then I'm going to sort them 70, 20, 10. And what's eigenvalue number 1 explaining out of all of them? 70%, because 70 divided by 70 plus 20 plus 10. The second one, 20%, the third one, 10%. So that's what we're doing here. You sort the eigenvalues and take eigenvalue divided by sum of eigenvalues, and that's what we get. 36%, 19%, and etc. These are the same numbers that we see here. This is the second method. The third method, so for these two, barely are going to use this method, because if it is PCA, you're going to use the built-in function from Sklearn or the PCA package. If it is kernel PCA, this method is not going to work. So for kernel PCA, which you're going to do in your homework, you have to do this way. If you want to find the PVEs for kernel PCA, you have to, so this is a third method that we are going to calculate PVEs. Let's see how we do that. We find the scores, right? But in the same dimension. So if our data set has 13 features, we're going to calculate 13 principal components. So you do not reduce the dimensionality of the data, right? And you look at the scores. Now, let's say I have 13 principal components, and you want to say principal component number 1 is explaining what part of the variation of the total data. If I take the variance of principal component number 1 divided by the total variance, that's the answer. Why do you think that's the answer? Because I'm saying that the variance of principal component 1 divided by variance of principal component 1 plus component 2 plus PC3 plus PC4. I'm not concerned about the covariance between PC1 and PC2. Why? If someone can help me with that. What's the covariance between PC1 and PC2? Let me help you out a little bit. PC1 is orthogonal to PC2. So what's the covariance? 0, right? So that's why if you look at the variance of PC1 divided by sum of, variance of sum which is equal to sum of variance, because these are orthogonal to each other, you get the proportion variance explained. You cannot do the same with x's, because variance of x1 plus x2 is different than variance of x1 plus variance of x2, because x1 and x2 are not orthogonal, but principal components are. So for that reason, this is a third way that you can do that. But you have to be careful that the number of components, you're not reducing the number of components. And you get the same numbers, 36, 19, and etc. So this is the only, well, at least as far as I know, the only way that works for kernel PCA. So if you want to construct, if you want to look at the, if you want to construct the Scree plot in a kernel PCA, you have to do it this way. And I don't know why they don't make it a built-in function. This is not that difficult, but, and then put it in Sklearn package, but this is definitely something that I'm not aware of, but we do it manually, so why not? So if you want to do it manually, this is how you do that. And then you can save them, you can manually construct a cumulative PVE and then plot them. So this is PVE, cumulative PVE. In the Scree plot, using the PCA package, it was a lot cleaner. You know, we have one bar here, one bar here, one bar here. Here we're using lines. You can change this from line plot to bar plot. You will see bars, but basically the idea is the same. So the first 4 components are explaining 70, let's say 7% of the variation, right? So this is how we do it manually. So the last notebook that I want to cover is the kernel PCA. So let's go over the kernel PCA. For kernel PCA, we're going to work with this social network ads data set. So if you're familiar with this one, this is at the end of the day, if the customers are going to purchase an SUV or not, right? And these are based on these characteristics: gender, age, and estimated salary, right? So let's go ahead and define our X feature, feature space. So we say age, estimated salary, and purchase or not. So this is the entire data set. I'm going to get rid of user ID and male. I will talk about the next class, why we end up getting rid of gender here. But just bear with me until next class. We're going to do a visualization and see why gender has no explanatory, not explanatory power, as is not informative enough for us to keep it in the model, right? We will discuss it next class. But for now, let's focus on age, estimated salary, and then purchase or not, right? So, guys, just to remind you that what we're doing, we're trying to replicate this one. We're trying to replicate this one, right? We know that the data is not linearly separable. We want to use kernel PCA, make it like this, and then apply a linear classifier. Let's say logistic regression, right? So let's go back. So I'm going to use logistic regression. The number of features is only 2. Yeah, well, we made it to be 2. We are using only age and estimated salary here just for visualization purposes. So let's quickly, from what we learned from the course, let's quickly build the logistic regression model. So from Sklearn linear model, we're going to import the logistic regression. We have to make sure that we standardize them. And then this is my target variable, purchase or not. This is the feature space, right? So there's only 2 features, age and estimated salary. Again, the usual supervised learning model, right? So let's say test ratio is equal to 20%, train is 80%. And then let's train the model, the logistic regression, train the model using the train data set. And then we can make prediction using the test set, right? So we have seen all these things before. Now, so this is the part that we want to transform this non-linearly separable data and visualize it in 2 dimension in PC1, PC2, and hope that that's linearly separable, right? So what should I do? From Sklearn decomposition, I'm going to import kernel PCA. And by the way, guys, this is not some kernel PCA is not something that it's available in PCA package. They haven't worked on it yet, but I assume that maybe in a couple of months, I don't know, maybe in 6 months or a year, it's going to be there. It's stable. As soon as they get a stable version of the code, they're going to release it to the public. But right now, it's not one of the features. So if you want to do kernel PCA, you have to use Sklearn. Okay, but I assume that it's not going to. It is not difficult to make it to just borrow it from Sklearn and apply to add it to this package. Okay, so if you want to do kernel PCA, we're going to import it from Sklearn decomposition, and then I call it KPCA, and this is an object called KPCA, and the function that we call from decomposition is kernel PCA. The documentation is the same, right? So if I look at the contextual help, what do we need for a kernel PCA? First of all, we need, I have to import it first. First of all, we need number of components. The kernel is linear or not. If I use kernel is equal to linear, this is exactly the same function as PCA, right? So you can try them and see that you get the exact same numbers. And then the discussion of RBF kernel, guys, remember what was gamma? That was the inverse of the variance. And we have, if it is polynomial kernel, we can use degree equal to 3 and etc. Right? So we have seen a bunch of these hyperparameters before, so I'm not going to spend time here. But that's the idea of kernel PCA is the same as support vector machine that we use. We saw the kernel function, kernel trick there. This is the same trick. Now we train the model, we make predictions in the test set. And now here's the difference. I'm training the logistic regression function. Now instead of X train, I'm training it on PC train. So the difference between these two models is that this is, I'm going to save them, give them different names, right? This is using logistic regression on X train and Y train. This is fitting logistic regression on PC train and Y train. Does that make sense? The features do. One of them is fitting a model in this space. One of them is fitting the logistic regression in this space. This is PC train. This is X train. Are we good? Okay. And then I save them. I give them different names. So for the predictions, I call them Y predict test and Y PC predict test, right, in the test set. Then you can look at the confusion matrix, at least in the train set. So if I look at the confusion matrix for, let me call them model number 1, and let's call them linear data, nonlinear data. So for linear data, the accuracy is 75%. For nonlinear data, but using PCA, the accuracy is higher, 87%. So this is good news. And then we can visualize it for the visualization purposes. So we're going to try two things: original space plus logistic regression. So basically this one. Second one, PCA space plus logistic regression, right? So PCA, well, let's call it kernel PCA space and logistic regression. So this is the visualization for the train set. And now we can look at the confusion matrix. Oh, well, we already looked at the accuracy, right? So the accuracy for the first one was 75%. For the second one that we use kernel PCA is 87%. And now visually, this is when we're not using the kernel PCA space, basically using X space, age and estimated salary. This is for the case that we are using kernel PCA. Yeah, something must be going on here because this line should be. I did it. Yeah, maybe because of the random state. This doesn't make any sense, right? This looks correct. And I took a snapshot of this picture from my Python. So I have to dig more, see what's going on. Let me give it one more try. And if I couldn't fix it. No, I don't. Well, we'll see. Because the numbers here are okay. Because the random state is different, I assume that that's the random state thing. Yeah, it worked here better. You can think of ensemble methods, average them out, and then report one number. Again, these are all things that you're familiar with. All right, that's pretty much it. So that was our discussion for the PCA. I hope that you realize how powerful this method is. It's very well established. I think we talked about it. It has a history of 120 years now. So it was developed 1901. And yes, I agree. It's not being used for the sake of dimensionality reduction these days because we have XGBoost and other more powerful methods that we necessarily don't need to reduce dimensionality that much. Given the fact that PCA is completely relabeling the data and we lose the, at least we lose the name of the features. But when it comes to using it as a pre-processing step to be fed into the more supervised and unsupervised models, still PCAs are powerful, right? You saw that how nicely we were able to say that one data set are 3 classes, 3 clusters. For your homework, you're going to work with a data set called customer malls. And basically you see the feature the dimensionality of the feature is very small, right? It's only 4. You look at the age of the customers of a mall, and you look at their income, you look at their spending score, right? If they how much they spend. I think there's these only 3 features, right? However, and imagine you want to work. So this is a homework. Actually, let's quickly read through the homework. This is an interesting homework as well. So imagine, let's see. Well, we can read through it. The data set contains information on age, annual income, and spending score. The higher, the more spending, right? Of 200 customers who regularly visit the mall, right? The management team of the mall wants to segment the mall customers, but they have no idea where to start from. This is very common, right? Because your data is not labeled. Imagine you have some data, you have no idea how to label customers. And they hire you as a data analyst to help them with their machine learning knowledge. From the machine learning course, you know that you have to do a clustering analysis on this data set. But before that, you need to do PCA to visualize the data into 2 dimensions. So eventually you want to decide what is the best number of clusters you should suggest to the management team. Is the question clear? So we are using PCA to, let's say, how many clusters do we need? And then based on that, say, for example, classify the customers into, these are potential, I don't know, high spending customers. These are something that you're not, you pass it to the marketing team, and the marketing team is not going to focus on these customers and then more focus on the other ones. We're going to talk about this homework more in class next time when we do clustering. So you're going to do homework, the PCA part. Next class, I'm going to do the clustering part, right? And we will compare. We will see, we can use this one as an input for our clustering method. All right, that was it. I hope that you enjoyed application of PCA in Python. And as always, let me know on the TAs if you have any other questions. Guys at home, are we good?
Yeah, thank you.
Okay, thank you.